Morning, everybody. We are Grace is Cool. I am the design lead, Skyler Knisely. To my right here is the prototype and documentation lead, Zane Winyard. And to my far right here is the testing lead, Peli.
So our guiding principles. First, our mission statement, which is enhancing the quality of life for amputees trying to reach new heights. And our vision statement, creating a cost-effective cooling solution that mitigates overheating which mitigates discomfort caused by overheating and friction at the limb-prosthetic interface for lower limb amputees.
So our challenge, lower limb amputees have lots of problems with heat buildup between their socket and their leg. That heat causes sweat, which causes leg swelling, which causes pressure points, which causes friction, which causes even more heat. It's a whole big vicious cycle. We want to clamp down at the source.
So our customer was lower limb amputees as opposed to upper limb amputees. And our customer also was active as opposed to the initial transition period of losing a limb when your body is still adjusting to its new cooling capabilities. So our first user need, the user needs the device to reduce and or eliminate overheating and moisture buildup where the limb and the prosthetic interact. So for this, our design input was that the device must reduce the skin temperature to a temperature range between 75 and 90 degrees Fahrenheit based on the source mentioned in the URL. Our user need 2, the device must not interfere with the use of the prosthetic in a significant way. And for our design inputs was the weight must be less than 3 pounds. User need 3, the user needs the device to survive active activities such as running, biking, rock climbing, etc. And for our corresponding design input here, we said that the device must withstand shock impacts from a 200-pound person running at 10 miles per hour for 5 hours. And this was based on the speed and weight of an average American male, and with an additional factor of safety built in by increasing the speed from the average 6 miles per hour to 10 miles per hour. For user need 4, the user needs the device to be a reasonable price. So for the competition, less than $1,500. And user need 5, the device must be easy to use. So the power batteries must be changed in less than 3 minutes.
So onto our device that we made to fill those design inputs and user needs. Here's our original concept, and back in the fall, basically a tornado socket of spiral air channels fed with a fan that would exhaust at the bottom. This is our prototype at the end of the fall. We have a little neck fan providing the airflow through that little black plate and through the channels down through the bottom of the socket. And here's what we have today. So we copied a existing pylon mounting design from the bottom of it. We have 2 blower style fans that take in air from the front and exhaust it out the top, just like your laptop cooling fans. All fed by a little battery through a distribution board into the channels. Here's a closer look at those channels. You can see them spiraling all down. You can also see at the bottom the exhaust channels to let the air out. And you might have noticed that it doesn't look a whole lot like a leg. Unfortunately, we could not conform it to the scan that you guys sent us. SolidWorks until it doesn't, and just would not play ball and wouldn't allow us to conform the device to the scan, despite numerous efforts. In terms of our budget, in parts, our device only cost about $116. And our entire project, including items needed for testing, we've only spent $510. Now going over the device itself, we have a small battery and a large battery with a small and large battery cover. You can see this area is broken. We'll get to that later. Otherwise, this would be completely covered. Simple switch to turn it on and off. And the 2 fans running up through this little catch to put it in through the channels. Air runs through the channels into these exhaust vents down at the bottom. And there you go. Not much to talk about there. In terms of commercial readiness, we think we have right about a score of 5.
So now I'm going to go through our risk analysis and our DFEMA chart. So for the first user need, again, the user needs the device to reduce and or eliminate the overheating and moisture buildup. So the input number that I'm going to highlight here is input 1.1. The device generates more heat than it takes away. And this would be the exact opposite of the competition goal and could lead to a possible heat stroke with an initial risk level of 4. To mitigate this, we would replace the cooling device that we had with a more efficient device. And to verify that, we are going to run our leg cooling capability test. User need 2, the device must not interfere with the use of the prosthetic in a significant way. So here, the input number that I'm going to highlight here is input 2.4. So the device causes the entire prosthetic to fall off, and the resulting harm, depending on the activity when this occurs, this could result in serious harm or even death with an initial risk level of 5. For the mitigation, copy existing attachment method or create a verification test to verify that the device will stay attached. And to validate this, we're going to use the device retention verification test. For user need 3, the user needs the device to survive active activities. And the input number that I'm going to highlight here is 3.6. The device breaks due to running shock loads. And the resulting harm would be it stops and or reduces the cooling effect, causing you to overheat. And then the mitigation here is to utilize a strong material with a well-designed housing for our batteries and cooling devices. And to verify this, we're going to use our MTS frame fatigue test. User need 4, the user needs the device to be at a reasonable price. So the input number that I'm going to highlight here is 4.3. And this says that the device is too cheap that it fails, and this will be a huge waste of time, effort, and money. And to mitigate this, we need to use a strong but cost-effective materials. And to validate this, again, we're going to use our frame fatigue test. User need 5, the device is too complicated to use, or it's too hard to adjust the cooling effectiveness. And the resulting harm would be that the user does not want to use the device, they don't like the product, then they'll become frustrated, want their money back, and want to go back to their old socket. And to mitigate this, we're going to provide a detailed user manual and have the test subject use the device.
So verification testing. As you can see on the right, there's a list of verification tests that we plan to go through. So the first test, the leg cooling capability, this one aimed to verify design input 1.1 and determine the steady state temperature by using a 25-watt aquarium heater.
So the results, we actually ran this twice, one for socket with small holes and one with socket with large holes, and both of them passed quite nicely.
So the second one, the pressure distribution simulation, this one we would have run on SolidWorks, but because as Zane mentioned before, we couldn't get the light to conform, that's why we did not run this test. So the third test, our MTS fatigue test, this one would basically simulate someone running at 12 miles per hour for 5 hours. And as you can see below, there's a list of parameters.
Onto the report, there were no breaks, cracks, deformities after the end of the test. The electronics still worked. The acceptance criteria was met. We succeeded.
So the impact test, this one was basically to simulate a 200-pound person running at 10 miles per hour and then falling onto the device itself.
Now this one we didn't do so well on, as mentioned before. And I will show a quick video to show what happened. So, had the pendulum set up. You can see the ladder move when we first release it. And kapow! So, that test was obviously a failure. Now to some minor tests, some little tests that didn't need a full protocol. The weight of our device was less than 2 pounds with the small battery and less than 3 pounds with the large battery, so we succeeded. In terms of battery life, the small battery had a capacity of 21 milliamp hours, Battery life of around about an hour and 45 minutes. Large battery has life of around 6.5 hours.
So validation testing. This was basically to prove that we had met our user needs. So the ideal test would have been ideally having an amputee wear the device and run or bike with it for 10 or 15 minutes. But we had to improvise.
So the alternative test we came up with was one similar to what you guys are going to run later, of have a dummy device and a functional device, and have someone, a non-amputee, test it out. And we had them answer a bunch of questions. A couple of them omitted because it wasn't quite representative of the ideal test. And we all passed for the questions that we actually asked. Now, more time and more resources. We'd really like to find an amputee that fits our project criteria. There's a big holdback. We tried, we contacted the VA people around, we didn't really get anywhere. Second main holdup was we couldn't confirm the device, as mentioned before. SolidWorks just wouldn't play ball. And because of that, we never developed a means to attach it to a patient's leg. And some other little minor ones. It'd be fun to make an app that displays your battery percentage, stuff like that. We had talks with a doctor, a prosthetist, I think that's how you pronounce it. And he was concerned about the squishy liner filling in the spirals. We couldn't investigate that because we ran out of time. And a couple of little ones. Haven't made a user manual yet, but again, that needs the prerequisite to that would be the means to attaching it to the leg, that sort of thing. So, for any questions, see our next video as we are currently graduating right now.